So now let's continue on and start talking a little bit about the list abstract data type, or ADT. So as a bit of review, remember from our first day of class, we talked about the idea of an ADT, abstract data type, being a description of what something does and not any one particular implementation. Think of this as an agreement on what should be provided, but not on the details of how to do it. So you might have many data structures, many ways of organizing data that comply with a certain ADT, a set of things it should do. And so, for example, in Java and in general, we have this idea of the list ADT that can be implemented with an array-based structure and also can commonly be implemented as a linked-based structure. There are certainly other data structures that exist out there that apply to this list ADT, but ArrayList and linked list are the two most common we talk about. So these data structures implement a particular ADT. And so this idea of a resizable array, which is we use as the data structure backing ArrayList in Java, can implement list, stack, queue, deck, and the priority queue interfaces, etc. It can really fit any of them. It might not do a good job at all of them, but you could potentially use it for a lot of them. And using linked nodes together to form a linked list, well, you could also use that to match these different ADTs for lists, stacks, queues, decks, priority queues, etc. We'll learn a lot about these other ADTs later. Right now, we're really just focusing on this list ADT. So our case study today is about the list. Why the list? Well, first off, it makes a really good point of review for CSE 143, since CSE 143 talks a lot about lists. You talk about lists in Java, and specifically the array list and the linked list. But a list in general, the ADT, it's the abstract idea, is a collection storing an ordered sequence of elements. So you have a bunch of elements starting from the beginning to the end. Each item has an index associated to it. So there's something at index 0, index 1, index 2, etc. And the list has a size. And the size isn't fixed. You can add things to the list, you can remove things, and the size of it will change. The size of it depends on the number of elements in the list. And it also allows you to add and remove elements in any order. So you can remove things from the beginning or the end. And I want you to think a little bit of the relationship here of the code that you might write that uses a list in Java with the mental model or the image of that list that you might form in your head. And so in Java, you can make a list by saying list of string names equals new array list. That's using the list interface, which remember an interface is Java's way of trying to define an ADT. And the data structure implementation ArrayList is one possible implementation of that interface. And you can ask for it to do things, like ask its size or add names. All of these methods you're calling on it are what the ADT can do. It says you can add things to it. You can ask what the size is. All of these are descriptions of what it does. And internally inside the ArrayList code, they figure out how you actually implement that stuff that you don't need to worry about from the perspective using something that abides by a certain ADT. And in some sense, the ADT matches really well to what you think of like your mental model of the state of the list. So when I add Leona and then add Ryan to the end and then insert Paul at the beginning, the contents of the list would be Paul, followed by Leona, followed by Ryan. Now, what you're thinking about, your mental model of the state, that's what the ADT tells you what happens when you do things to it. It tells you what you should think of when a data type of this abstract data type is being used. Different implementations might actually store the physical bits on the computer in different ways. But we don't worry about that from the perspective of the ADT. All we worry about is operations and what you're allowed to do with your data. Okay. So, continuing our case study, let me define what the list ADT is. It has some state, which is the set of ordered items, so element 0, element 1, element 2, and it has the number of items. It knows how many elements are in it. And it has behaviors like get an item at an index, change an item at a particular index, add an item at the end, insert an item at an index, delete an item at an index, and figure out the size. Now, the list ADT corresponds to the list interface in Java, which has methods for all of these things. And in Java, it provides concrete implementations of these through the Arraylist class and the linked list class. And as a reminder, the approach the Arraylist does is it tries to implement the list ADT, the list interface. It's going to store a sequence of values with indices that you can add and remove things. Its strategy for actually representing that data is to use a really roomy array. To use an array that's bigger than how much data you need. And then, so if you had a list that represented 3 numbers, you would store the 3 numbers, but you might have extra room out there at the end. And all of your operations, the concrete implementations of the operations, work on that array. Okay? Well, your linked list implementation does something wildly different. It uses these linked nodes that you probably remember from CSE 143, where you have a node at the front that links to the next node, which links to the next node, and the state of the list that we think of as being the list 88.6, followed by 26.1, followed by 94.4. In this abstract terms, on the left, we really implement this as a series of linked nodes. Both of them are just different implementations of the same idea. So let's focus a little bit more on the Arraylist for most of our discussion. So how does Java actually go about implementing Arraylist to achieve this list behavior? I just mentioned to you on the inside, it stores an array. That array has some fixed capacity. It's a certain size. And that array typically will have more space than what's currently used. So when you actually first create a new array list in Java, and on the outside view, you ask its size at 0, well, internally it's storing an array, which if I remember correctly, starts at 10 long. There's 10 empty spots. And as you add things to your list, your outside view of the thing adds these values. But internally, while it's still adding them, it still has all that extra room in the back. And it's essentially hiding that from you. It's abstracting away the details of its implementation so that when you view what it's doing, you can think about it in terms of that list ADT. And so it stores all these elements in the front of the array and keeps track of how many there are, the size. So you don't get confused that these nulls at the end or any of the spots at the end are actually empty. So you need to know how many of these rooms are actually filled up. And that means because we're storing all these in the front, like if you wanted to remove Paul, you would need to move all the other elements over. And that, you can imagine, might be a cause of slowdown. And we'll use our lens of runtime analysis to maybe compare Arraylist and linked list. And so to give you a little bit more visual on this idea of this requirement of all the elements being at the beginning and having the roomy array at the end, actually causes some shifting that needs to happen. So suppose I had this list that represented A, B, C. And remember, internally, it's going to have an array that might be much larger. In this case, much larger is 4 elements or 4 spots. I want to insert D at index 0. Well, it needs to start by shifting all of the elements over so that I could then write D safely in the first spot. And by doing so, all state must be updated. So it also must update the size. So the size must be updated to 4. Now, say you want to delete something at an index. So say you want to delete something at 0. Well, now, if you want to remove the first element, which is D, well, now we need to make sure those empty spaces end up at the end. So we need to shift everything back to the left. So everything will move back to the left. And then we decrease the size to 3. Now, all of this shifting, you might be able to tell, might be a cause of a slowdown, and we'll actually think about how to analyze that. But the first thing I want you to think about is in this remove operation, this delete operation, when we're shifting everything over, do we have to delete or overwrite what used to be at index 3 with a null or some empty value? I want you to think about, should we do this? And I want you to explain why. So item pool will pause and ask you to type in a response. We're not going to have a correct answer for this one because it's going to be a paragraph or a couple sentences. But I'll explain after you hit submit some ways of thinking about this. Okay, so hopefully you had a chance to type something in. And remember, the important thing here is to explain why or why not. So it turns out for this question, the answer is yes and no, or both. It depends. Whenever a lot of times we're going to be faced with questions of, should I do this? And the answer is, well, there's trade-offs. So in some way, you don't need to overwrite that 3. It's not strictly necessary. The reason is it's the job of the array list to make sure that from the client's perspective, outside of the array list, that we're creating this illusion that even though this array inside is really big, well, you only get to see the first size elements because those are the only ones you know are in there. And in our implementations, we generally don't assume that everything outside of our size is null. If we're going to add a new element in there, well, we'll just overwrite it. We never require that there's nulls there to keep track of where the end is. We use size to keep track of that. So it's actually not strictly necessary to remove a value there. But it might actually be necessary to remove it. So a lot of really big security bugs, when you think about like some low-level software that operates really closely to your hardware, a lot of these security vulnerabilities come from the fact that people took advantage of the fact that you don't necessarily need to remove these values, but then they might leave important, crucial, security-critical information behind that then someone can go look at if they get access to the bits on the computer. And so maybe from a security standpoint, it is a good idea to null things out because you might not want any bad actors to see any old data that might have been deleted. And so there's trade-offs here because, you know, nulling something out takes a little bit of time, and it may or may not be necessary based on your context. And so this is what we mean by when we talked about thinking about design decisions on the first day, is there's usually trade-offs, and trying to articulate why a trade-off might be more important to you based on your context is a very important tool. Now, one other edge case I want to talk about when we're thinking about implementing array lists is thinking about what happens if I want to add elements to my array list, but I run out of space in my roomy array. So suppose my array inside my array list only had 4 elements in it, and I put 4 things in it, and I want to add a new thing. Well, one behavior you might think could be, well, maybe it just crashes, but we probably don't want the client code to just break because we ran out of space. So the trick that we do here in the array list world, which you may or may not have seen in CSE 143, it usually depends on the quarter if there's time to cover this. We do a special trick where we just make the array bigger and then copy everything over. So if you ever run out of space in your internal implementation of the array list, it will just make a new array for itself that's much bigger and copy everything over, and then it'll be happy because it has a roomy array. This is called a resize operation. It's actually a very common trick in some, not all, but some data structures. Now what this means then is appending to an array list is generally really fast when there's still room left, because you just add things at the end. That's really easy to add things to an array. But once you run out of space and you need to do a resize, then it's going to be a really slow operation. You're going to have to make this bigger array, copy everything over, get rid of the old array. That could slow down your program. And so we'll actually talk about how you analyze these cases when, you know, sometimes it might be a fast operation and sometimes it might be a slow one. Now, before we go and talk about design decisions and kind of thinking about how we talk about runtimes for all these various operations, I want us to think about one more thing. So I talked a lot about array list. I didn't talk too much about linked list. So remember linked list, we have our nodes that are linked together and it has a reference pointing to the front, and then you use those links to figure out the order of the list. Think about a situation where it might be much faster to use a linked list than it is to use an array list. So try to think of a situation and explain why that is. Okay, so hopefully you got a chance to explore something. Again, there's no correct answer here. There's lots of possible situations potentially, or maybe you said none. One example I can think of is adding and removing values to the front of the array, the list. Remember, with the array list world, we have to do all this shifting. If you add something at the front, you need to shift all the other values over. If you remove something from the front, well, you have to shift all the values back. With linked lists, though, all you need to do is just change the front pointer to be to the new node and have that node point to the old front. And if you remember kind of all those tedious linked list operations you did in CSE 143, while it maybe is not the easiest code to write, it is very efficient because you just change a couple lines. You don't have to do any looping over your data just to modify the front. This doesn't mean linked lists are always strictly better. There are lots of situations where ArrayList might be preferred, and that's where we're going to get into our next video talking about design decisions. How do I think about comparing these two? But I want us to start with this as kind of a warm-up for that.